equal to Pearson's. Non-parametric equal to S. Yes, non-parametric equal to S. Pearman. Correlation done. Next talk. Yes, my dear. Once again, the non-parametric heading. You got a data, non-parametric. You got a proportions and percentages. Compare. So you need to do the squat. And the squared test equal to proportions or percentage. So this is the summary boxes, my dear, that you need to know. To know the significance test, my dear. So somebody talk once again the parametric, non-parametric. Parametric data means the measured data, the student status before and after. Non-parametric, the Coxon compare before and after. Correlation parametric Pearson's, non-parametric S. Pearman. Non-parametric square equal to proportions and percentage. So once again, the significance test, my dear, the box that we have made that are really helpful. We're going through the different boxes here. So here is also written two simple, one way, ANOVA, two way, no need, and parametric versus non-parametric test. You can go through one start this box, and also summary of the parametric test applied for different type of the data. So we called it the compare the two paired group, two unpaired data, and compare the three or more matched group, the two way ANOVA, and going to the three or more matched group. Here's the one way ANOVA, correlation between the two per Pearson. And non-parametric test, number of the factors, sample, Wilcoxon signed rank. The sample is also 1 star or less than 1 star. Is also less than 1 star. Yes, my dear doctor. So summary box that we have already made, the parametric. Once again, the student status before and after. Student status is a normal distribution, is a measured data. And non-parametric, once again, that you need to learn the box. This is very important, my dear. So non-parametric, the Coxon is a compare before and after. And correlation, once again, the parametric data, the Pearson's, non-parametric, once again, S. Pearson. And non-parametric score, the C-score test is a square. Square means the proportions and percentage. So that we can focus on to the questions, and that will be really helpful. Next topic, my dear, correlation and linear regression. Correlation and linear regression is a double star topic, my dear. The terms correlation and regression are related but are not synonymous. Correlation is used to test for association in between the variables where the salary and IQ are related. Once correlation between two variables has been shown, regression can be used to predict values of other dependent variables from independent variables. Regression is not used unless two variables have firstly been shown to correlate. So correlation is used, so the correlation to test the association between the variables. So associations with the salary and IQ are related. So correlation is a relation. Once correlation in between two variables has been shown, regression can be used to predict. So regression is a predict values of other dependent variables from independent variables. Is not used unless the two variables have firstly been shown to correlate. So we can make a box here. So correlation equal to association. So correlation equal to association. And regression equal to yes, the predict the word prediction. So correlation is an association. Correlation is an association. The way I'm writing, just follow me. Correlation is an association, and regression is an prediction. Correlation, the degree of correlation, is summarized by the correlation coefficient. So correlation coefficient is an R. This indicates how closely the points lie to a line drawn through a plotted data. Means how closely. Close correlation. In a parametric data, this is called the Pearson's correlation coefficient. We already learned the parametric data, Pearson's correlation coefficient. And can take any value in between the -1 to +1. Can take any value -1 to +1. For example, R equal to 1 minus strong positive correlation. If it is +1 equal to strong positive correlation, means the systolic blood pressure always increases with age. 0 equal to no correlation. There is no correlation in between the systolic blood pressure and the age. And -1, what does it mean? The strong negative correlation means the systolic blood always decreases with age. So correlation coefficient, the 1, +1, 0, -1, having the strong positive, no correlation, and strong negatives. Correlation coefficient. Before going to these more details, I would like to go to some of the questions. A study is performed to assess the correlation between the age and systolic blood pressure. Which one of the following statements regarding the calculation of correlation coefficient is incorrect? Incorrect. May be used to predict systolic blood pressure for a given age. My dear, can you remember the regression is a predict or predict? So regression is a predict. I said the correlation, remember the correlation is an association and regression is a predict or prediction. So prediction can be done by the regression or linear regression. Now the correlation coefficient only shows the associations. So some of the linear regression is need to the predict. So correlation versus regression. So this is the correlation and this is regression. Simple linear regression. So here is written, you see the regression builds on a relationship from correlation. The purpose of regression are prediction and expansion. So the word prediction. The regression requires that the correlated variable be separated into an independent variable and a dependent variable. Simple linear regression determines the best fit straight line. So simple linear regression determines, you see determines the best fit straight line that represents a set of data. Simple, there is only one independent variable. Linear, the relationship is a straight line and y equal to mx plus b. No need, but the linear regression is a prediction, my dear. Now get back here. So correlation coefficient, the measure of the strength of the line of the best fit. Correlation coefficient, the word is a correlation of the strength of the line best fit. So you see the correlation coefficient values is a no correlation. You see the data are just dispersely distributed. At plus 0.5, the weakly positive, but strong positive 0.9, and the perfect positive, you see there is a linear patterns. In contrast, the minus is a weak negative, more negatives, and here is a minus 1 is a perfect negative. So one is a perfect positive correlation. This one, 0 no correlation, the values don't seem linked at all, if it is something like that. And minus 1 is a perfect negative correlation. Whilst correlation coefficients give information about how one variable may increase or decrease and another variable increases, they do not give information about how much the variable will change. They also do not provide information on the cause and effect. So correlation only shows the associations. Increase or decrease another variable increases. So here is a strongly positive. It does mean the systolic blood pressure always increases with age, and systolic blood pressure decreases with age. So that perfect negative. Correlation is summarized when using the parametric variables by the Pearson's correlation coefficient, represented by a small r. In this situation, in the non-parametric variables, Spearman's correlation coefficient is used. Spearman correlation coefficient is usually represented by the Greek letter P, RHO, rho, or by RS. So once again, the summary talk, my dear. The correlation coefficient is the strength of the line of the best fit. 1 plus 1 is a perfect positive, 0 no correlation, and minus 1 is a perfect negative. Make a box, my dear. And in parametric data, the correlation that we can show the correlation, systolic blood pressure increases with age, systolic blood pressure decreases with age. So this correlation in a parametric data, P for parametric, P for Pearson's correlation coefficient, that can be R, small r, and non-parametric data Spearman, that we are putting the P or RS. So Pearson's is an R and Spearman's is a small r. So we can make a box here. So correlation coefficient, relation coefficient. Correlation coefficient equal to parametric, as we already learned, equals here parametric data for the Pearson's, and we called it R, small r, and non-parametric equal to Spearman. Spearman's, and that is represented by small p. So yes, my dear doctor, small r, and this is small p. So sometimes let's vary the r and p. So this is the box, my dear. In this case, the dichotomous variables logistic regression is used. In the case of dichotomous variables, logistic regression is used. Linear regression is used when looking for association in between the two continuous variables. So linear regression, two continuous variables. So the two continuous variables. Multiple regression is used when looking for association in between the more than two continuous. So multiple regression is more than two continuous variables. Linear regression, in contrast to the correlation coefficient, the linear regression may be used to predict the single word, how much one variable changes when a second variable is changed. A regression equation may be formed equal to y equal to a plus bx. So a regression equation, y equal to bx. So y equal to bx, it does mean y equal to a plus bx, y equal to the variable being calculated, a equal to the intercept value when x equal to 0, b equal to slope of the line of regression coefficient, simply put how much y changes for a given change in x equal to second variable. You don't need to know this linear regression calculation equation, no need at all. Just remember the linear regression for the prediction and correlation for associations and correlation. So here is the term, the correlation between the age and systolic blood pressure is incorrect, so it may be used to predict. No, prediction by the linear regression. Simple linear regression is builds the relationship from correlation and purposely gives the prediction and explanation. Now the funnel plot is another topic, is the funnel plot, my dear. Funnel plot is a double star topic, is primarily used to demonstrate the existence of the publication bias. What I say, the funnel plot is primarily used to demonstrate the existence of bias. So here's the publication bias. Funnel plot is a bias in a meta-analysis. So funnel plots are usually drawn with the treatment effects on horizontal axis. So circle the treatment in a horizontal axis and study site on the vertical axis. So means in a y-axis the study result and x is the treatment effects. So a symmetrical or inverted funnel shape indicates the publication bias is unlikely. Bias is unlikely. So funnel plot is nothing but to demonstrate the existence of the bias in meta-analysis. So the bias, so if the symmetrical, bias is unlikely. If it is unsymmetrical, the funnel indicates the relationship between the treatment effects and the study site. This indicates either publication bias or a systematic difference in between the smaller and larger studies. Small study effects means the bias is there. So in an x-axis, there you put the treatment effects, and in y-axis, there you put the study size. So funnel plot. So you see the symmetrical, so the no bias. Asymmetrical, you see the dots are more and more, so this is asymmetrical, so the bias is there. Publication bias is there. So the questions here, what are the funnel plots primarily used for? So simple talk, the funnel plots are used for the bias, my dear, in a meta-analysis. So the bias, the single word. So we can make a box for the funnel plots. Yes, the funnel plots. Funnel plots. Plot equal to bias. And once again the symmetrical equal to no bias, and asymmetrical equal to yes, bias. So yes, these are the three important talks that we need to remember. The funnel plot is a bias, S equal to no bias, AS means asymmetrical is yes bias. So final plus show the publication bias in the meta-analysis. Next topic might be the hazard ratio. And you see the hazard ratio photo is written the decreased risk of heart failure or sudden cardiac death, increased risk of congestive heart failure or sudden cardiac death. Some of the parameters are written there. Hazard ratios. Interpreting the hazard ratios often interprets a relative risk. Not technically the same. Hazard ratio compares risk of event in two populations or samples. Ratio of risk in group 1 to risk in group 2. So the risk ratio. So here, between the group differences measure the estimates of the celecoxib and saxagliptin studies. Celecoxib and saxagliptin. Hazard ratio. You see the hazard ratio here, 3.35. Within the bracket is written something, and 1 is a saxagliptin. Now the questions. Which one of the following types statistical measure is most important to compare survival time with? So compare the survival time. Statistical measure, the survival time. A study is performed comparing the two chemotherapy regimes for the patients with small cell lung cancer. The endpoint of the study, survival time. So the answer is the hazard ratio. So hazard ratio is similar to relative risk, but it is used when the risk is not constant to the time. But is used when the risk is not constant to time. It is typically used when analyzing the survival over time. So my dear, just make a box for the hazard ratio. So yes, the hazard ratio. Hazards means the risk ratio. We call the relative risk. And this is not constant to the time. Equal to not constant to time. So we called when it is measured the survival time. So yes, my dear, the hazard ratio is nothing but the survival time. HR, survival time. Hazard ratio, hazards, survival time is nothing but the relative risk. Relative risk, but is a survival time. Survival time. Hazard ratio, survival time. So we can get back to the hazard ratios topics here. So here is written to compare the risk of event in two populations of the or groups, means the relative risk as well we can say, and ratio of the group in group 1 and group 2, hazard ratio. So simple word that you need to remember, that the statistical measure is done for the hazard ratios is for the survival time. Screening test statistics might be a 5-star topic, might is a very hot topic of the exam, and you need to know them very well. Some of the formulas are really important for calculating some of the mathematical problems so that you can get them very well. The screening test statistics, the patients and the doctors need to know if a disease or condition is present or absent. Once again, the patients and doctors need to know if a disease or condition is present or absent. So that's why we do the test. Can be used to help us decide. Tests generally guide us by indicating how likely it is that the patient has the condition. So that we need to do the test. And the word, the screening test, we do the test, my dear. we need to diagnose, and we need to including the diagnosis, and sometimes you need to excluding the diagnosis. So that's why we do the screening test, and these statistics we need to know very well. In order to interpret the test results, we need to have the working knowledge of statistics used to describe them. And for this one, there is a contingency tables. Yes, the contingency tables, also known as the 2 into 2 tables. 2 into 2 tables, you see the 2 into 2 data are used to illustrate and calculate the test statistics such as sensitivity. It would be unusual for a medical exam not to feature a question based on screening test statistics. Commit the following table to memory and spend time practicing until using it. It will be expected to make the calculation using it in your exams by then. So here is some of the keywords: the true positive, true false positive, true negative, and false negative. People going to this contingency table, I'd like to see some of the questions here. A new screening test is developed for the colorectal cancer. It is blood test which detects a protein. The higher level of the protein, the more likely the patient is to have the colorectal cancer. If the cutoff for a positive test is increased, which one of the following will also be increased? Positive test is increased, which one of the following will also be increased? There is a specificity. The answer is specificity. Increasing the cutoff positive test results will decrease the number of false positives, and hence the increases the specificity. So this is very important. Increase the cutoff of a positive test results will decreases the number of false positives. So decrease the number of false positives, and hence the increases the specificity. So cutoff positive test results is important. So if it is increasing, increasing the positive test results will decrease the number of false positive, and hence the increase the specificity. So the word is an increase the cutoff test results, increases the specificity. Increase means the cutoff and specificity. The two important words that you need to remember here, we'll see later on. So another question is that a rapid finger prick blood test to help the diagnose the DVT is developed. Comparing the test to current standard techniques, a study is done on 1,000 of the patients. DVT present, DVT absent. New test positive in 200 patients, and DVT present in 200. DVT absent is 100, but the test is positive. New test negative, but DVT is present in 20. New test negative, but the DVT absent also 680 patients. So what is the specificity of the new test? So 680 by 780. Specificity equal to true negatives divided by true negatives plus false positive. So you need to calculate and get the right answer. 680 by 780. Another question. What is the correct formula to calculate the positive predictive value? So you need to know positive predictive value here, the true positive divided by false positive and true positive altogether. Another question. A new blood test to screen the patients for the heart failure is trialed on 500 patients. A new blood test to screen the patients with the heart failure. Feel that with the BNP levels, heart failure is trialed in 500 patients. The test was positive in 40 out of 50 people shown to have heart failure by echocardiography. It was also positive in 20 patients who were shown not to have the heart failure. So what about the positive predictive value of the test? So same questions here. What is the positive predictive value of the test? So yes, my dear doctors, so knowing some of the formula will be helpful to calculate the desired questions. So this contingency table, just we need to know what does this TP means a true positive, FP for false positive, TN for true negative, and FN for false negative. Right, very simple. Test positive, disease present. So this is called the true positive, the test. We got a test results positive and the disease is present. So this is called the true positive. Disease absent but the test positive. This is false positive. We called it false positive. Test negative, disease present but the test negative. Disease present but the test negative, the false negative. Disease absent and the test negative, and definitely this is a true negative. So summary talk, disease present and positive, test positive, is a true positive. Disease negative means the disease absent and test negative is a true negative. So my dear, you'll have the mathematical questions. So you need to make a contingency table fast before calculating your desired questions. So what we need to make the test positive, test negative, disease present, disease absent, and we'll put the true positive, and here is the true negative, and of course this is the false positive, the test positive but the disease absent, the false positive, and test negative, the false negative, but the disease is present. Like we do a test, dengue NS1 antigen, dengue serology. Dengue is present, the test is positive, NS1 positive, so this is a true positive. Dengue absent, but NS1 positive in some other diseases, so these are false positive. So once again, NS1 test negative, but the disease is present, means the dengue is there, so this is a false negative. Once again, the disease is absent, means the dengue is absent, NS1 negative, so of course these are true negatives. Now we need to know these one. The table below the list the main statistical terms used in relation to the screening test. So we need to know this sensitivity, my dear. Sensitivity is the word working on the proportion of the patients with the condition who have the positive test results. The sensitivity is all the positive test results that we are working. And specificity, basically the patient without the condition who have the negative test results. So we're working on the negative test results. So sensitivity equal to the positive, as I said, the true positive divided by true positive plus false negative among them. True positive divided by true positive means the positive along with the falsely negative. The disease is there but the falsely negative. So among them, how much the true positive patients are there. So this is called the sensitivity. So summary talk, the single talk, the sensitivity equal to true positive divided by true positive plus false negative. Specificity is just a negativity, negative test result. So true negative divided by true negative. Once again the false positive. Positive predictive value, the word you see, the positive predictive value, I'm giving you tips. All are positive, you see. True positive divided by true positive plus false positive, and negative predictive value is all are n's, you see. But the true negative divided by true negative plus false negative. So now you can get them very well. So I'm asking now the question, the sensitivity is nothing but a positive idea. So true positive divided by true positive but plus false negative. Specificity is nothing but the negatives test result. So true negative divided by true negative plus false positive. Now the positive predictive value all are positive. So true positive divided by true positive plus false positive. And negative predictive value once again is a true negative divided by true negative plus false negative. All are n's. So get them by heart, my dear. Positive is the chance that the patient the condition in the diagnosis test is positive. Chance and diagnosis test is positive. So same here, negative, the chance the test is negative. So how to do calculate? So once again, sensitivity is a test of positivity. So true positive divided by true positive plus false negative. Specificity is a test of negative test result. So true negative divided by true negative plus false positive. Positive predictive will all are positive. So true positive divided by true positive plus false positive. Negative predictive value. So once again all are negative. True negative divided by true negative plus false negative. Measure another one, the likelihood ratio for a positive test results. So likelihood. So as I said, the positive test means the sensitivity. So sensitivity divided by 1 minus specificity means the sensitivity. Just circle the sensitivity. Positive test results is the sensitivity. Is a negative test results, once again the 1 minus sensitivity divided by specificity. So likelihood ratio the positive to how much positive test result, how much the odds of the disease increase when the test is positive. Here is how much the odds of the disease decrease if the test is negative. So likelihood ratio means the odds. Just remember, positive test results, if the test is positive, odds of the disease is increase. How much? So here is the likelihood ratio for a negative test results. If the test results is negative, the odds is decrease. Odds of the disease decrease. Positive and negative predictive values are prevalence dependence. So the circle of negative predictive prevalence dependent. Likelihood ratios are not prevalence dependent. So yes, not prevalent dependence. So positive and negative predictive values are prevalence dependence. And likelihood ratios are not prevalence dependent. So we need to write down the predictive values equal to prevalence dependent and likelihood equal to yes, not prevalence dependence. So predictive prevalence, likelihood not. Precisions quantify the test ability to produce the same measurements with the repeated test. So precision, what does this precision means? Quantifies a test ability to produce the same measurements with repeated test. So precision, they produce the same measurements. Positive predictive is a probability that the subjects with the positive screening test truly have the disease. Negative test is the subjects with the negative screening test truly don't have the disease. So this is the contingency table. So now here the important things. The question said that if the cutoff is increased, positive test is increased, which one of the following will be increased? The cutoff for positive test is increased, and this increases the specificity, the single word. So cutoff increase equal to specificity increase. Box my dear. And here is the question, the specificity of the new test. So if the contingency table is given, so this is easy to do. So you need to make your specificity equal to, I said the specificity is nothing but the negative. So true negative divided by true negative plus false positive. So true negative is a 680 is a true negative divided by true negative means a 680 plus once again false positive. So false positive means the test is positive, is 100, so 780. So 680 by 780. So here's the true negative, so this is the answer. What is the kind of positive predictive value? So positive predictive value is nothing but the true positive divided by true positive plus false positive. So yes, positive predictive value of the test. So you need to do the contingency table first. So like this, the heart failure, no heart failure, test positive, test negative. So 40, 20, 10 and 430. So you need to make them fast so that we can make the positive predictive value 0.66. Same here, the positive predictive, you need to make the contingency table fast before doing the calculations, my dear. So summary talk, my dear, is really important. The boxes that we've already studied, the sensitivity, specificity, and the contingency table, the screening test, statistics. So yes, the sensitivity is nothing but positive test, true positive divided by true positive plus false negative. Specificity is the negative test results. So specificity is the true negative divided by true negative plus false positive. Positive predictive, all are positives. True positive divided by true positive plus false positive. Negative predictive value is nothing but all negatives. True negative divided by true negative plus false negatives. Next is the likelihood ratio. Likelihood ratio of positive test results equal to sensitivity divided by 1 minus specificity. And likelihood ratio for a negative test results, so once again 1 minus sensitivity divided by specificity. Positive test results increases, negative test result decreases. Positive and negative predictive means the predictive value is the prevalence and likelihood ratios are not prevalent dependent. Screening Wilson and Younger criteria. So it is written, when establishing a screening program, which of the following is not a key criteria defined by the Wilson and Younger double star topic matter. So screening test, yes, screening Wilson and Younger criteria is said that the 10 criteria is there here. I just made some of the bold lines. So the public, treatment, facilities, symptomatic, natural, test, acceptable, policy, cost and continuous process. So screening program should be potentially curable. No, it's nothing like that. So the condition should be an important public health problem. There should be an acceptable treatment for the patients with the recognized disease. Facilities for diagnosis, treatment should be available. There should be a recognized latent or early symptomatic stage, natural history of the condition, suitable test, acceptable test and examination acceptable to the populations, and there should be a good policy and a great policy to whom to treat, and cost of case finding should be economically balanced within the possible expenditure as a whole, and case finding should be continuous process, not a once and for all project. So these are the words that you need to remember: public, treatment, facilities, symptomatic, natural, test, acceptable policy, cost continuous. So you can make a box, my dear, so that will be helpful. So I'm writing the public, treatment, facilities. So say with me the public treatment facilities. Next is symptomatic, natural, symptomatic, natural, then the test acceptable, symptomatic, natural, test acceptable, test acceptable, And next, policy, cost, continuous. So these three groups of words that you need to know, my dear. So this is double star topic that you need to know. The public treatment facilities, symptomatic, natural, test acceptable, policy, cost continuous. Concept of experimental event rate, and once again the control event rate. So this is also the double star. Experimental event rate, this is a rate at which the events occur at the experimental group. Experimental event rate. Control event rate, the event occurs in a control group. So experimental event rate equal to the number who had the particular outcome with the intervention divided the total number who had the intervention. Experimental group. Control number who had the particular outcome with the control, and number who had the control. So experimental event rate and the control event rate. Relative risk. Relative risk is the ratio of the risk in the experimental group to risks in the control group. So relative risk is nothing but the experimental is a risk ratio, is a ratio. So relative risk is the ratio of experimental event rate to risks in the control group, means the control event rate. Experimental event rate and control event rate. The term the relative risk ratio is sometimes used instead of relative risk. So relative risk ratio. So relative risk is nothing but the risk ratio, means the ratio of experimental event rate and control event rate. We'll look at the trial comparing the paracetamol for dysmenorrhea compared to the placebo. We may get the following results. Paracetamol, total number of the patients 100, placebo is 80. Experience significant pain relief with the paracetamol with the 60, and in placebo only 20. So experimental event rate equals here 60 divided by 100. So 60 pain relief divided by 100 is the paracetamol number of the total patients, so 0.6, and control event rate is a 20 by 80 equal to 0.25. So the risk ratio equal to the experimental event rate divided by control event rate equal to 2.4. So relative risk ratio. If the risk ratio is greater than 1, then the rate of an event, in this case experience a significant pain relief, is increased compared to the controls. It is therefore appropriate to calculate the relative risk increase if necessary. The rate of an event, in this case experiences significant pain relief, means the greater than 1. If the risk ratio is less than 1, then the rate of an event is decreased compared to the controls. The relative risk reduction should therefore be calculated. Means, once again, whenever the relative risk is greater than 1, so we need to relative risk increase, another term should be calculated. Same thing, if the risk ratio is less than 1, the relative risk reduction should be calculated. So we have got the relative risk is nothing but the, once again, summary box, experimental event rate divided by control event rate. And if it is greater than 1, so relative risk increase, greater than 1 increase, so the increase should be calculated, and risk ratio is less than 1, so relative risk reduction should be calculated. Which one of the following statement regarding the relative risk is correct? Answer is usual outcome measure of cohort studies. So cohort studies, a box that we need to remember, equal to the relative risk. Remember, the risk and odds are different. If 20 patients die out of every 100 who have a myocardial infarction, then the risk of dying is 20 by 100. whereas the odds are 20 by 80 equal to 0.25. Means the risk ratio, relative risk and the odds are different. If the 20 patients that die out of 100 who have the macular infarctions, the risk of dying is 20 out of 100. But the odds will be out of 20 divided by 80. A new drug is designed to prevent the exacerbation of genital herpes undergoes a clinical trials. 100 of the patients are given in the new drug. During this 3 months period, the 10 out of the patients have an episode of genital herpes. In the control group, there are 300 patients who are given a placebo. In this group, the 50 people have an exacerbation during the same time of the period. What is the relative risk of having an exacerbation of genital herpes whilst taking the new drug? So this is 0.6. How to do that? We done the experimental event rate equal to 10 by 100, 0.10, control event rate equal to 50 by 300, and relative risk equal to 0.1 divided by 0.16 is to 0.6. So the next term, the relative risk reduction or increase is calculated by dividing the absolute risk change by the control event rate. Using the above data, so relative risk increase or reduction is the experimental event rate minus control event rate divided by control event rate. 0.6 minus 0.25 divided by 0.25, 1.4, 140%. Relative risk reduction. So yes, my name is triple star once again. The questions so that you can get the data for the relative risk. It's triple star. Once again, the relative risk. Absolute risk reduction. Yes, once again, equal to the control event rate minus experimental event rate or experimental event rate minus control event rate. If the outcome of the study is undesirable, then the absolute reduction rate equal to control event rate minus experimental event rate. If the outcome study is desirable, then we need to remember absolute reduction rate equal to experimental event rate, control event rate. This may be more accurately termed the absolute benefit increase rather than absolute risk reduction. So this is another question, so very simple calculation, 5%. And next, the number needed to treat is once again the triple star topic, my dear. Number needed to treat is a measure that indicates how many patients would require an intervention to reduce the expected number of outcomes by 1. It is calculated by 1 divided by absolute risk reduction and is rounded to the next highest whole number. So here is in questions. Absolute risk reduction that we can make the experimental event rate and control event rate. So experimental event rate and control event rate minus. So this is the difference, absolute risk reduction. So 1 divided by absolute risk reduction rate equal to number needed to treat. So here is also the maybe used to the number needed to treat, absolute risk reduction. Next question is written that approx how many were the risk of adverse cardiovascular outcomes needed to be treated, number needs to be treated. So what do you need? Absolute risk reduction. Absolute risk reduction, what does it mean? The control event rate and experimental event rate. the differences. So that we can get it. So the same questions. Next, the odds and odds ratios. Odds, another triple star topic, my dear. The odds are a ratio of the number of the people who incur a particular outcome to the number of the people who do not incur outcome. This is a measure of association between the exposure and an outcome. The odds ratio may be defined the ratio of the odds of a particular outcome in the experimental treatment and that of control. Means the odds ratio equal to odds of disease in exposed, disease in the non-exposed. Like here in examples here. The total number of the patients 60 paracetamol is given. Achieved 50% of the pain relief is 40, placebo 90 and 30. The odds of achieving the significant pain with the paracetamol. So odds of disease in exposed means the 40 divided by odds of disease in the non-exposed is the 20. The 40 by 20 with placebo, so 30 by 60 equal to 0.5. So therefore the odds ratio will be the 2 divided by 0.5 equal to 4. So the odds ratio and relative risk these are the two different ways that we need to calculate. So odds ratio, just to remember, exposed divided by non-exposed, my dear. A box for the odds ratio. OR equals odds ratio exposed divided by non-exposed. So the exposed divided by non-exposed. So 40 divided by 20 divided by 60, and ratio just exposed divided by placebo. So odds versus probability. The probability is a fraction of times you would expect to see an event in many trials, while expressed in a single number, probability is always between 0 and 1. Probability 0 and 1. So if you take the examples of rolling a dice, the probability of rolling is a 6 is 1 by 6, the 0.16 is 6. The odds of rolling a 6 is a 1 by 5, the 0.6. Odds ratio are the usual reported measure in the case control study. So odds ratio is a case control studies. It approximates to the relative risk if the outcome is interest is there. For example, if you look at the trial comparing the use of the paracetamol for dysmenorrhea compared to the placebo, you may get the following results. So all of the achieving significant pain and also achieving therefore the odds ratio. So what I'm saying, my dear, one of the important box that I need to remember, odds ratio equal to is needed for the case control study. Case control. So OR, all case control, odds ratio is the case control study. And here is an odds ratio, the calculation. So let's go through them. So this is one important point. For the odds ratio, very close approximate to the relative risk. If the outcome interest is rare. And the question, so that you can odd ratio, odd ratios, and also the odd ratios, and also odd ratio, and the calculations for the weighted risk and hazard ratio, similar to the weighted risk but used when the risk is not constant to the time. And what does the power of the study equate to? Power equal to 1 minus probability of type 2 error. So this is in the box. Incidence and prevalence. I would like to give one box, my dear. The PID means the prevalence equal to incidence into the D for durations. So this is very important, mind. The prevalence is the duration of the condition. Chronic disease prevalence is greater and acute prevalence